Most developers treat the Java virtual machine as an opaque execution box. You deploy a jar, allocate some RAM, and trust the runtime. But at high scale, the physical overhead of byte code verification and memory synchronization creates rigid performance boundaries that an opaque model cannot account for. We can see the specific cost of these boundaries by finishing our analysis of the virtual thread per task execution pattern. When you initialize an executor via new virtual thread per task executor, you are building an unbounded engine. It maintains no core pool size, enforces no maximum limit, and holds no internal task queue. For every single task submitted, the engine instantly spawns a brand new isolated virtual thread, mapping thousands of them concurrently across a small pool of underlying native carrier threads. Many architects attempt to constrain these lightweight units inside a classic bounded array queue. This introduces severe artificial lock-contention and infrastructure tracking overhead into a system that was designed for frictionless scaling. Traditional native threads require pooling to mitigate their heavy creation and scheduling costs. Virtual threads are user mode data structures, physically designed to be used once and discarded immediately after execution. Applying legacy constraints to disposable components generates useless processing bottlenecks. To optimize throughput, engineers must look past the API and map the actual physical boundaries of the JVM. The first boundary is the entry gateway, the Class Loader Subsystem. This component reads compiled class byte streams and constructs the native metadata footprints used by the engine. This progression begins with Phase 1, loading. The JVM resolves the binary stream representation of a class using a strict structural hierarchy known as the Delegation Model Matrix. This matrix relies on 3 distinct loaders. At the base is the application level for custom code, moving up to the platform level for extended APIs, and finally the bootstrap level, written in native code to handle foundational runtimes like java.lang. The rule of this matrix is upward delegation. A loader must pass the request to its parent first. It will only parse the raw byte code itself if every parent loader reports that it cannot locate the class. This upward first execution path acts as a hard defense mechanism, preventing external payloads from overriding core platform classes. Once the bytes are located, the process moves to Phase 2, linking. It starts with verification, a high-security binary check that ensures the code complies with Java language specifications and cannot introduce memory corruption. Next is preparation. The runtime allocates off-heap native memory for static fields and sets them to their default primitive values, mapping integers to 0 and object references to null. Linking ends with resolution. The JVM navigates the internal constant pool, converting symbolic string markers and method signatures into direct physical memory reference addresses. Finally, we reach Phase 3, initialization. The JVM actively executes all static code segments and variable initializations by bundling them into a single synthesized method known as Clinit. This 3-phase progression is strictly sequential and protected by internal locks, ensuring the code is fully verified and initialized before it ever interacts with the dynamic runtime. Once loaded, an application state is distributed across memory partitions dictated by strict thread accessibility boundaries. On one side are the thread-isolated memory zones. Because these locations are restricted to a single thread, operations here carry 0 synchronization overhead. The program counter, or PC register, tracks the exact native instruction or byte offset currently being processed by the active thread. Adjacent to this, the Java thread stacks hold local primitive variable allocations inside isolated frames. Pushing and popping these frames requires 0 mutual exclusion locks. The requirements change when we move into shared memory spaces. Here, multiple threads converge, making concurrent coordination mandatory for every read and write. The primary shared partition is the Java Heap. This is the transactional footprint where all object instances are allocated, making it the central target for garbage collection workflows. Surrounding the heap is Metaspace. Replacing the legacy permgen, Metaspace resides outside the heap boundaries within off-heap native OS memory. This partition dynamically resizes to house the structural metadata, immutable class blueprints, method tables, and the runtime constant pool. By storing metadata in native memory, the JVM isolates the static blueprints of the application from the volatile object allocations filling the heap. This separation prevents metadata-heavy workloads from competing for heap space. though it shifts the management of class structures into the operating system's native memory pool. To maintain these shared spaces, the system relies on garbage collection. These are a set of mechanical constraints strictly required to reclaim memory without stalling the underlying processor cores. Modern heap design is guided by the weak generational hypothesis, the empirical observation that the vast majority of allocated objects die shortly after they are created. The young generation segments into 3 regions: Eden and dual survivor spaces S0 and S1. When Eden fills, a minor collection clears dead references. Survivors move into S0. On the next cycle, survivors from both spaces compress into S1. This continuous ping-ponging compaction mechanism eliminates memory fragmentation on the fly, avoiding the need for CPU-intensive sorting across the entire heap. Objects that survive a specific number of these cycles, controlled by the max tenuring threshold, are promoted into the old generation. While the young generation design processes high-throughput data efficiently, the persistent state in the old generation requires more costly major GC cycles, forcing a choice between different collection strategies. A senior engineer's selection of a garbage collection engine directly dictates a service's production latency and throughput profile. Parallel GC, known as the throughput collector, treats memory generations as monolithic blocks during its cleaning cycles. This results in significant stop-the-world pauses. The collector halts all application threads to perform its sweep, creating latency spikes that scale with the size of the heap. While parallel GC is ideal for offline batch processing, G1 GC divides the heap into thousands of independent regions. It tracks and cleans the most garbage-dense areas selectively within a target time window. This targeted scope allows operators to set an explicit maximum pause time, making G1 GC the standard for enterprise web services with large memory requirements. For systems requiring even lower latency, ZGC is designed to handle heaps up to 16 terabytes while maintaining consistent sub-millisecond pauses. ZGC executes marking and relocation concurrently with application threads. It uses colored object pointers and load barriers to intercept reads, patching the reference address instantly on the fly, avoiding execution freezes entirely. Scaling modern enterprise architectures requires moving past high-level abstractions. Success at scale comes from mapping precise memory boundaries and aligning your garbage collection strategy with the physical requirements of your system.